Hello students, in this short video lecture I am going to discuss the result. An order isomorphism is a bijection but the converse is not true. Now in this particular video we are going to use two concepts, the concept of a partially ordered set or a PO set and the concept of an order isomorphism from one PO set to another PO set. Now both these concepts have been discussed in details in my earlier videos. I have already defined what a PO set is along with the examples have been taken in my video, and the other concept, which is the concept of order isomorphism, that also has been discussed in a video along with examples. So but just for the sake of this particular video, let me recall these two concepts. What is a partially ordered set or a PO set, and secondly, what is an order isomorphism from one PO set to another PO set, and then we will come to the actual result which we have to discuss in this particular video. And now recalling what is a PO set, if P is a set on which a binary relation less than equal to is defined, then we say that P is a partially ordered set or a PO set if it satisfies three properties: reflexivity, antisymmetry, and transitivity. Now we say that reflexivity is satisfied in P if every element x belonging to P that we choose, if we find that x is related to itself, if every element of P is related to itself, then we say that reflexivity is satisfied. Then coming to the second property, antisymmetry, we say that antisymmetry is satisfied in P if for every pair of elements x and y that you choose from P such that x is related to y and y is related to x, that is, first is related to the second element and the second element is related to the first element. If this collectively implies that x is equal to y, then we say that antisymmetry is satisfied. That is, first element is related to the second and if second element is related to the first, then if this implies that the two elements are identical, and for any pair of elements that you choose from x and y which are satisfying these two properties, if this is satisfied, then antisymmetry is satisfied. Then coming to the third property, transitivity, we say that transitivity is satisfied in the set P if for every three elements x, y, and z belonging to P that we choose such that x is related to y and y is related to z, if this implies that x is related to z, then we say that transitivity is satisfied. That is, if first is related to the second and if second element is related to the third, if this collectively implies that the first element is related to the third element, where these three elements are coming from the PO set P, from the set P, then we say that the set P satisfies the transitivity property, and if all the three properties, reflexivity, antisymmetry, and transitivity, are satisfied, then P is said to be a PO set or a partially ordered set. So this definition of a PO set or a partially ordered set has been discussed already in my earlier video, and also we have taken a few examples. So if one is interested in reading or learning more about partially ordered set, one can just refer to that particular video. Now coming to the second concept, which is the concept of an order isomorphism from a PO set to another PO set. So let me take two PO sets. Let P less than equal to and Q less than equal to be a PO set, where this particular less than equal to, or this particular binary relation is a relation on the set P, and this particular less than equal to is a binary relation on the set or the PO set Q. And if psi is a map from P to Q, then psi is said to be an order isomorphism if psi satisfies two properties. Psi must be an onto map. Saying that psi is an onto map means that if we pick up any y belonging to Q, which is the codomain, if we pick up any element y belonging to Q, then we must be able to find some x belonging to P such that psi x must be equal to y. This means that every if pictorially if you see, psi is a map from P to Q. This is the case. If we pick up any y belonging to Q, then we must be able to find some x belonging to P such that the image of x under psi must be equal to y, which in other words means that every element y belonging to Q must have a pre-image x belonging to P. This must happen for a map psi to be onto. This is the first condition that must be satisfied, and the second condition that must be satisfied for a map psi mapping from P to Q to be onto is that for every pair of elements that you choose from the set P, pictorially let me just describe this particular condition. If you have, this is the case that this is your set P and this is your set Q, this is P, this is Q, and if you pick up any pair of elements X and Y belonging to P, then if let us suppose that X is related to Y, suppose this is the case that X is related to Y, then the image of X under the map psi and the image of Y under the map psi, they should also be related, which means that something like this should happen. If X is related to Y in P, then this must imply that their images psi X and psi Y, these two also must be related in Q, and also the opposite must happen, which means that if the images are related in Q, then the elements must be related in P. So both the ways it should happen. So if condition 1 and condition 2 both are satisfied, then you say that the map psi mapping from P to Q is an order isomorphism. So again, as I said earlier, that I have already discussed the definition of an order isomorphism in detail in my earlier video along with some examples. So if one is interested in knowing more about order isomorphisms, one can always refer to that video which discusses order isomorphism along with examples. So now with these two definitions in hand, that is the definition of a partially ordered set or a PO set and the definition of an order isomorphism, the result that has to be discussed in this particular video is that every order isomorphism is a bijection, but converse is not true. This is what I have to show. And again, coming to what a bijection is, bijection, we already know, we have already been referring to this particular word, which is a type of map. You say that a map psi, a mapping from P to Q, is a bijection if it satisfies two conditions. The map psi must be 1, 1 and the map psi must be onto. Now onto I have already discussed. When do you say a map to be onto? Now when do you say a map to be 1, 1? Pictorially this can be discussed easily. If this is the set P and if this is the set Q, and if psi is a map from P to Q, and let me pick up two elements X and Y over here in P, and their images psi X and psi Y, their images are of course here in Q. So if you have that if psi X is equal to psi Y, if the images are equal, if this implies that the elements X and Y are equal, if this is the case, then you say that the map psi is onto psi is 1, 1. This is one way of defining a map to be 1, 1. That if the images psi X and psi Y are equal, if psi X is equal to psi Y, this implies X is equal to Y, then psi is 1, 1. Or the other alternate way of defining 1, 1 map is that if X is not equal to Y, if this implies that psi X is not equal to psi Y, which means that if the elements X and Y in P are distinct, and if this implies that their images are also distinct, then you say that the map is 1, 1. Because suppose if this doesn't happen, if X and Y are distinct but psi X is not equal to psi Y, and let's say psi X is equal to psi Y, then if the map has to be 1, 1, then this should imply that X should be equal to Y. But this is not happening. X is not equal to Y. X is distinct. X and Y are distinct. So, so this is an alternate way of actually defining map to be 1, 1. Either you can define a map psi to be 1, 1 like this, which means that if the images are equal, then the elements are equal, or you can define a map to be 1, 1 like this, that if the elements X and Y are distinct in P, then if this implies that their images are also distinct in Q, then the map is 1, 1. If any of these two things are satisfied for any pair of elements that you choose from X and Y, then you say that the map psi mapping from P to Q is 1 1. So with these definitions in mind, that what do we mean by a 1 1 map, what do we mean by an onto map? If a map is both 1 1 and onto, then it is said to be a bijection. So all we have to do is we have to show that an order isomorphism is a bijection. But the converse is not true, which means that a bijection need not be an order isomorphism. This is what we have to show. So let me take two PO sets P and Q, and let me take an order isomorphism from P to Q, and I will just show that this order isomorphism psi, let's say mapping from P to Q, that is a bijection. So that is what we are going to show. So P and Q are two PO sets, and this is a binary relation on P, this is a binary relation on Q, and psi is a map from P to Q, and psi is an order isomorphism. All we have to show is that psi is a bijection. Now, which means that I have to show that psi is a 1 1 and onto map. These are the two things that we have to show. Now psi is given to be an order isomorphism, and I have already recalled the definition of order isomorphism. An order isomorphism is a map which is onto and which also satisfies this condition, which means that if the elements are related in P, then their images are related in Q, and if the images are related in Q, then the elements are related in P. Both the ways it is true. So psi, we had to show that psi is a bijection, which means that these are the two conditions we had to show, that psi is 1 1, psi is onto, but psi is already onto by definition of order isomorphism. So the only thing that remains to show is that psi is 1 1. So in order to show that psi is a bijection, we just need to show that psi is 1 1. So this is the case that you have P and Q are the two sets, the two PO sets, and psi is a map from P to Q, and now you have to show that psi is 1 1. So what we do is that we pick up two elements x and y belonging to P, and accordingly the image of x under the map psi is psi x, and the image of y under the map psi is psi y. And let me suppose that psi x and psi y are equal, and these are elements in Q. Psi x and psi y are elements in Q. So let me suppose that psi x is equal to psi y. I just have to show that psi x is equal to psi y implies x is equal to y. If I am able to show that psi x is equal to psi y implies x is equal to y, then this automatically means that psi is 1 1. This is the definition of a 1 1 map. So let psi x is equal to psi y. Now we know that psi x and psi y both are elements in Q, and Q less than equal to, this is a PO set. So and we also know that in a PO set reflexivity holds. So this means that psi x, because psi x is an element of Q and psi y is an element of Q again. So psi x is related to psi x. Psi x is related to itself because of reflexivity, and psi y is related to itself. Psi y is related to psi y because both are elements of Q, and Q is a PO set. Now this psi x, this particular psi x, I just replace this psi x by psi y because I know that psi x and psi y are equal, and this particular psi y, this particular psi y I replace by psi x because I know that psi x and psi y are equal. So this is what you have. Psi x is related to psi y and psi y is related to psi x, just by replacing this particular psi x by psi y and this particular psi y by psi x. So again we know that psi is an order isomorphism, and by the definition of an order isomorphism, whenever the images are related, then the elements are related. So psi x less than equal to psi y implies like x is less than equal to y. Again psi y is less than equal to psi x, the images are related implies the elements are related. So y is related to x. So these are the two conclusions that we get. X is related to y and y is related to x, but x and y are both elements of P, and P is a PO set, and in a PO set reflexivity, in a PO set antisymmetry holds. And antisymmetry means that if first element is related to the second, and if the second element is related to the first, then both are identical, which means that x should be equal to y. So what are we getting? We started with this particular expression, this one, and we are getting the last expression. So I don't need the mid steps in between. I just write that the first step and the last step, that psi x is equal to psi y implies x is equal to y. This is what we are getting, and this is nothing but this is the definition of a 1 1 map. So psi mapping from P to Q is a 1 1 map because whenever the images are equal, this implies that the elements are equal, so psi is 1 1. So we have marked this as star dash, and psi, as I already said, psi is already onto, we have marked this as star. So psi, so star says that psi is onto, star dash says that psi is 1 1. So psi is both 1 1 and onto, which means it's a bijection. So what we have proved in this part is that a map psi mapping from P to Q, which was taken to be an order isomorphism, that has come out to be a bijection. So this is one part of the result that we had to show, but we had to show that the converse is not true, which means that if you are given a bijection from a PO set to another PO set, it is not necessary that it will be an order isomorphism, which means that the converse of this result is not true. So in order to show that the converse of this result is not true, let me consider an example. I'm taking an example in which the PO sets P and Q both are same, and I'm taking my P and Q both to be equal to the set consisting of two elements 5 and 6, and the binary relation less than equal to is the usual less than equal to relation, the usual sense in which we understand less than equal to relation. Now we know that both the PO sets P, both the sets P and Q are PO sets, because we know that actually 5 6 this is a subset of set of reals, and the set of reals with respect to the usual less than equal to relation, this is a PO set. We already know that, we have done when we were discussing the PO sets, and since every subset of a PO set is a PO set with respect to the inherited order, so this means that the set 5 6 with respect to the inherited order less than equal to, which is the usual less than equal to relation, this is also a PO set. In fact, the set of real numbers is a chain. A chain is a PO set in which every element is related to the other. So if you pick up x and y to be any real two real numbers, then we know either x will be related to y or y will be related to x. Here less than equal to is the usual less than equal to sign, the usual sense in which we understand less than equal to. So R is not only a PO set, it is more than a PO set, it's a chain. And also we know that every subset of a chain is a chain with respect to the inherited order. Now because 5 6 is a subset, this set consisting of two elements 5 6, this is a subset of R, and R less than equal to is a chain. So this set 5 6 with respect to the usual less than equal to sign, this is also a chain. So basically it's more than a PO set. This is what I'm trying to say. So but for this particular example, we just need a PO set. So P and Q are taken to be same, equal in this case, and P and Q are taken to be sets consisting of only two elements, that is 5 and 6. So this is the case that we have, that you have P, if diagrammatically if we try to visualize, this is the set P, this is the set Q, and P consists of two elements 5 and 6, and Q consists of two elements 5 and 6, and both are PO sets. In fact, both are chains with respect to the usual less than equal to relation. Now what we do is we define a map psi mapping from P to Q as 5 is mapped to, let's say, 6. This is how we are defining it, and 6 is being mapped to 5. So this is what how I define psi 5. The image of 5 under the map psi is 6, and the image of 6 under the map psi is 5. So we can see that this particular map, this is onto. Why? Because every element here in Q has a pre-image. The pre-image of 5 is 6, and the pre-image of 6 is 5. So this is an onto map. Also this is 1 1 because as I said earlier, that a way of showing that a map is 1 1 is that if the elements here are distinct, as in this case 5 is not equal to 6, we can see that their images psi 5 is not equal to psi 6. The images are also distinct because psi 5 we know is 6 and psi 6 we know is 5. So if the elements are distinct, their images are also distinct, which means that the map psi mapping from P to Q is a 1 1 map. So from this discussion we have that the way we have defined the map psi, that this particular map is also a 1 1 map, and it is also an onto map, which means that it is a bijection. So psi is very much a bijection, but I claim that psi is not an order isomorphism. Psi is not an order isomorphism because you can just see that if you 5 and 6 are elements in P, and 5 and 6 are also elements in Q, and we can see that if we pick up these elements 5 and 6 in P, we know that 5 is less than equal to 6, which means 5 is related to 6, but this does not imply that their images, which is psi 5 and psi 6, are related. These are images in Q, and these are elements in P. They are not related. The elements are related, but the images are not related, because by the way we have defined psi 5 is 6 and psi 6 is 5. So 6 less than equal to 5. This is not true. So this means elements are related, but the images are not related, since the second condition for a map to be an order isomorphism, this was the second condition, that a map psi mapping from P to Q is an order isomorphism if whenever the elements are related, the images are related, and whenever the images are related, elements are related. Both the ways it must be true. If because this is not being satisfied, so psi here is not an order isomorphism. So here is an example of two PO sets and a map psi mapping from the PO set P to the PO set Q, such that psi is very much a bijection, but psi fails to be an order isomorphism, which means that it is not necessary that a bijection will always be an order isomorphism. So this is what we have concluded in the whole discussion, that an order isomorphism between two PO sets will definitely be a bijection. We have already proved it, but converse is not true, because we can have bijections which may fail to be order isomorphism. So a bijection from one PO set to another PO set might not be an order isomorphism. So that is what I had to discuss in this particular video.